Everybody for coming. And thanks very much to both Wei and Benoit for inviting me to speak today. I really have very much enjoyed these sessions on soft matter. I think they're fantastic, and I really do hope that we get to continue these on going forward, regardless of how COVID is influencing everything. So I thought I'd tell you a little bit today about some of the research which has been going on in my lab in the general area of trying to control properties of monolayers by using fluorinated and perfluorinated surfactants. Now, the outline that Wei gave of my research program is a little bit out of date, which reminds me I need to update my webpage. But in general, we are a lab which does physical chemistry research. We're based at the University of Saskatchewan, which is more or less in the geographic center of Canada. And so we carry out research in a couple of different areas in my lab. One of the major topics of research is looking at properties of monolayers, surfactant monolayers at the air, water, and solid air interfaces. These are some of the general snapshot of some of the various projects that we've worked on over the past few years, a number of years now. So we've done some work in trying to use perfluorinated surfactants to control properties of phospholipid monolayers. We're primarily a physical chemistry experimental group, but we dabble once in a while in computational methods. So we've done some work in terms of simulating things like phase separation processes. And just over the past 5 years or so, we've been using some X-ray diffraction-based methods, things like GIXD and X-ray reflectivity, primarily with Wei at the Advanced Photon Source, to try to characterize structures of some of the films that we've been looking at more of a crystallographic and molecular level. So that's the surfactant end of my research program. We also have a active second branch of research in my lab where we're using optical spectroscopy to characterize really energy transfer in photoexcited systems. Most recently, I've been doing quite a bit of collaboration with my colleague Ron Steer at the University of Saskatchewan. We've been looking at things like triplet annihilation, photon upconversion processes, photoexcited systems. Now, it's fairly rare that the two branches of research in my group kind of overlap, but very recently we've started to work on a project where there is some overlap between our surface chemistry interests and our spectroscopy interests. And so we'll talk a little bit about this near the tail end of my seminar today. Okay, so moving into the main subject at hand. One of the major research interests that we've been pursuing in my lab over the past few years is trying to use fluorinated and specifically perfluorinated surfactants to control and regulate properties of monolayers and primarily structures of monolayers. So I think most people, in fact, everybody in this audience, I'm sure, is familiar with the many standard hydrogenated surfactants. So fatty acids, for example. I think perfluorinated surfactants are maybe a little bit less well known. So perfluorinated surfactant is, well, just choose your favorite, let's say fatty acid and swap out all the hydrogens for fluorines. So there's a perfluorinated surfactant. So it turns out that fluorinated and perfluorinated surfactants are actually excellent surfactants. They are very good at lowering surface tension of water. They spread very rapidly at the air-water interface, and so they've got excellent thermodynamic and kinetic surface active properties. Now, these are interesting molecules from many perspectives, and these have been reviewed a number of times in literature. This is kind of an interesting review, the article that I like to look at from time to time, this one from the early 2000s. There's a couple of really interesting physical properties of fluorinated molecules that are worthwhile talking about. Now, one is structure. So if you think about a standard, let's say hydrogenated, an N-alkyl chain, for example, the chain of a fatty acid, we know that in a hydrogenated alkane, we typically have sort of the classic zigzag chemical structure. But you see something a little bit different with perfluorinated chains. And so if you've got a perfluorinated alkyl chain, we actually get a very different structure. So by virtue of the relative steric bulk of fluorine and its relatively high electron density, the structures of perfluorinated chains tend to be helical. Okay? They're helical. They also tend to be mechanically extremely rigid. And so this can actually impart some really interesting, and in some cases, very useful properties to perfluorinated surfactants. Okay. Now, perfluorinated surfactants in general under many conditions turn out to be immiscible when you mix them with hydrogenated components. Fluorocarbons in general are often immiscible with hydrogenated components. I sometimes like to use a really terrible analogy to describe this when I'm talking to undergraduate students. This is not a good analogy, but I think it's kind of an entertaining one. And I say that the incompatibility of hydrocarbons and fluorocarbons is very similar to what happens if you put a droplet of cooking oil on a nonstick frying pan. So a nonstick frying pan, if you've ever seen or used these, this is basically a piece of steel. You kind of sandblast this, you graft some sort of, let's say, fluoropolymer onto its surface. And so this is your fluorocarbon. Your cooking oil, well, that's basically like a liquid hydrocarbon. And if you put a droplet of this oil on your nonstick frying pan, what you'll find is that the oil does not wet the surface. That is, it sits on the surface with a relatively high contact angle, unless you turn the heat up. And so in general, we say that this is kind of an example of how hydrocarbons and fluorocarbons are immiscible. Now, sometimes a word which is used to describe properties or this property of fluorocarbons in general is lipophobicity. We say that the fluorocarbon is lipophobic. And that's really a word which I admit freely that I probably used myself, but it's really not a good explanation of really the underlying physics or physical chemistry of what's going on here. So if you look at this a little bit more carefully, there we go. It's really a better way to think about this is that it all comes down to polarizability. Now, I'm a chemist, and so I'd like to think about properties of matter from a molecular point of view, but you can kind of map this equally well into physics space if you're a physicist or what have you. But in general, perfluorocarbons are amongst the least polarizable molecules that are out there. If you map this using the Lorentz equation into physics space, you can say that we have extremely low refractive indices of these materials. So we have very low polarizability, low enthalpies of vaporization. And so this has some actually fairly profound implications. So if you think about this from the perspective of simply things like very basic dispersion potentials, interaction potentials between molecules, you can choose your favorite interaction potential here. If you use the London dispersion potential, that gets you somewhere useful. But in general, these interaction potentials are going to scale as the square of the polarizability of the molecule. So what are the implications of this? Well, the implications of this are that perfluorinated molecules generally are not going to be attracted particularly strongly through dispersion forces. Okay. So now if you think about this from the point of view of mixing this with hydrocarbons, the implications are fairly clear. So if we've got a bucket of hydrocarbon and fluorocarbon, what's essentially going to happen is that the relative strong dispersion forces in the absence of other complications, all of the hydrocarbons will stick together. And the fluorocarbons, which have got comparatively weak dispersion forces, well, those are going to be basically excluded. And so it's not a situation where we have lipophobic, we're not pushing, our fluorocarbon is not pushing the hydrocarbon away. It's simply that the hydrocarbons are going to kind of stick together and the fluorocarbons generally just will be excluded because of this difference in polarizability. So that's really a better way that we should kind of think about this a natural tendency for these two components to not mix. Okay, so that's in general, in broad strokes, what's going on. So how does this tie into surfactants? So let's talk about this from the point of view of surfactants. Well, it turns out that very often, if you mix a hydrogenated and a perfluorinated surfactant, they don't mix, and they actually can give you some relatively interesting behavior. So we've been looking at this for a number of years from many different types of systems, but I think kind of a nice way to illustrate this general effect is by looking at simple fatty acids. Okay? So let's start off this kind of discussion with just a simple binary mix system. So let's say that we've got a fatty acid, long, greasy hydrocarbon chain, got a carboxylic acid head group here, and we're going to mix this with a relatively simple perfluorinated fatty acid. So let's take this guy, perfluorotetradecanoic acid, slightly shorter chain. And again, remember this is mechanically rigid, but also attached to a fatty acid head group. Okay, so what happens if you mix these things together? Let's just do some relatively straightforward experiments. So we'll mix these together in monolayers. What happens? Well, we're a group who does a lot of Langmuir-Blodgett, Langmuir-Monolayer type of work. And so let's look at some isotherm results. Okay, and so here's some isotherms of this relatively simple binary system. And so here in the black, we've got the isotherm for pure behenic acid. Here in this pinky fuchsia color, you've got the pure perfluorotetradecanoic acid. And in between the two of them, we've got various mixtures of the two with these different mole fractions. So these are mole fractions of the two. Okay. So the fatty acid, there's nothing new under the sun. We see all of the usual phase transitions. Perfluorinated, well, that's a compound that's fairly simple as well. Mixtures fall more or less in between the two extrema of those two pure components. Okay, now if you dig into the details of the isotherms a little bit more, there's some additional interesting information here. Now, it turns out that the mixtures of the two of these guys does not behave as a simple additive mixture. It doesn't behave like a thermodynamically ideal mixture. We don't have a simple linear combination of the two components in terms of the total area of the mixed films. So you can kind of see that in this diagram here. If this dotted line here is just a simple additive relationship, the mixed films have areas which are larger. So basically the films are more expanded than we'd expect from a pure additive ideal mixture of the two components. Okay. So if you like this lipophobic term, which you probably shouldn't, but chemists tend to fall in love with these types of expressions, you can kind of imagine that the two components are being pushed away and the films are more expanded. We probably shouldn't think about this again in terms of pushing away, but the films are certainly more expanded in terms of their mixtures than the pure individual components. Okay, so fair enough. That kind of seems reasonable enough. What are the implications of this in terms of film structure? Well, the implications of this in terms of film structure are really quite interesting. And so if you take these mixed monolayers at the air-water interface, you deposit these onto some sort of solid substrate, and you image these in, let's say, your atomic force microscope, these are the types of images that you get. So you get these really interesting phase-separated domains. We call these hexagonal domains or polygonal domains, surrounded by some sort of C, some sort of matrix around it. And so it turns out that these hexagonal domains here, or these polygonal domains, are the hydrocarbon component, and the surrounding C is the perfluorinated component. You can kind of extract this by basically measuring heights if you're reasonably careful and with your AFM. And so basically the height difference between these polygonal domains and the surrounding ocean corresponds to the length difference between the basically normally absorbed or vertically absorbed, if you like, surfactants on a solid interface. Okay, now you should always be, of course, a little bit skeptical of AFM imaging. And so if you don't believe the chemical recognition element of this, you can try other more sporting approaches. This is a TOF SIMS, basically a surface mass spectrometry map, slightly different length scale. But you can see that the dark regions here, which correspond to these basically discontinuous domains, these other images are low in terms of fluorine content. Basically, the surrounding ocean is enriched in fluorine. So these are the hydrogenated components here surrounded by fluorocarbon. Okay, so that's actually kind of interesting. So can we actually kind of understand what's going on in terms of these systems, in terms of why we're getting these domain formations, why we're getting the types of domains that we're seeing? Well, there's a couple of elements here. There's both the size and the shape of these domains. Let's talk a little bit about the overall size of these domains. Now, the nice thing about simple fatty acids is that you basically got a chemical handle which you can use to kind of play some interesting games. And so what I'm showing you in this slide here is really kind of the accumulation of a number of different projects that we've done over the years, is kind of tying this all together. But what we're doing in this, or I'm showing you in this series of images, are surface structures where we have kept the perfluorinated component constant. So we've kept this guy constant, and we've systematically varied the tail length of the fatty acid. So back here, we had this behenic acid, the C22 component. Here we're going progressively shorter and shorter. And what you find is that you get a systematic change in the overall, if you like, lateral extent of these phase-separated hydrogenated domains. Okay? And so as you go to shorter and shorter chain length, you've got a tendency to form these these larger domains in terms of lateral extent. And so can we understand what's going on here? Well, yeah, we've actually got, I think, a reasonably semi-quantitative understanding of what's going on here. And so you can kind of describe this by using some of the classic models that were put together for single component systems by Hart and McConnell back in the early 90s. Okay? And so I'll kind of skip over some of the gory details here. But the basic idea is that you've got really kind of an interplay between dipole-dipole repulsion and line tension between your different phases. So you can kind of think of it this way. If we've got all of our head groups, let's say we have negatively charged head groups in the case of these fatty acids, which is is pretty much what we've got under the conditions that we're using. If we start jamming those head groups a little bit too close together, then we're going to have a tendency to kind of push out, to push those head groups apart. Now, it's a little bit more complicated than that, of course, because we also have to worry about dipole packing density in the surrounding phase. But nonetheless, we're going to have a tendency to increase the lateral extent of these systems. But likewise, at the same time, we've got interface between our two different phases. And of course, there's a line tension term in the overall free energy of the system. And that's going to have a tendency to kind of draw this down to the minimal line of contact between our two different phases. And so really what we're looking at here is kind of an interplay between these two different effects. And so if you go back to these systems here, what we've done is we've kept the dipoles constant. So to a first approximation, this term remains fixed. And so effectively what we're doing by changing the chemical composition here, by changing the chain length, is we're effectively kind of manipulating this line tension term through dispersion forces. Okay? So as we're going down to shorter and shorter chain length, we're basically favoring the formation, or basically favoring this tendency for this lateral extent of these guys to increase. Again, just by kind of playing games with the chemical composition of the system. Okay. So that's the type of thing that you can do with these perfluorinated mixed systems. You can kind of manipulate the general composition to really get some degree of control and understanding over the overall film structure. Now, that's fine in terms of, if you like, equilibrium geometry. And then those models by McConnell were essentially thermodynamic models. Now, that's all well and good. But what about these shapes? So we're talking about lateral extent, but what's giving rise to these interesting shapes that we see? Now that's actually a really interesting story in and of itself. The early thinking that we had in terms of the overall shapes, why we're kind of forming these polygonal domains in these fatty acid systems. Originally, what we had thought was that the solid substrates that we use in these types of systems, so if we deposit our samples onto, say, mica or glass, was in some way, shape, or form templating these structures onto the solid interfaces. That turns out not to be the case. So this is a Brewster angle microscope image of one of these phase-separated fatty acid films. And even at the air-water interface, you'll see that we still get these same types of polygonal domains, the same kind of interesting structures. Okay? So we're not templating this, at least with the solid substrates. There's all sorts of other interesting bits and pieces you can see here. You can see these different shades of gray in those domains, which basically corresponds, these different textures that we see, which basically corresponds to not thickness variations in the films, but rather different, if you like, azimuthal tilt angles of the molecules which comprise these domains. Now, really interesting. This actually seems to be a more general feature that you see in mixed fluorinated hydrogenated systems. Many of you might be familiar with these so-called semi-fluorinated alkanes, basically these primitive surfactants which have got blocks of fluorinated and hydrogenated components in the same molecule. And in those systems as well, where you've got both fluorocarbons and hydrocarbons in the same molecule, you actually have a tendency to form some of these absolutely beautiful hexagonal types of structures. There are different mechanisms going on there, I think. But certainly this is actually a fairly common feature that we see in these mixtures of fluorinated and hydrogenated systems. And so we wanted to try to get a little bit of a handle on why we're seeing these really interesting types of shapes that we're seeing. And so relatively recently, we've started to use synchrotron-based techniques. And so we're relatively new with synchrotron techniques. What we've been working with the folks at the Advanced Photon Source. We first did these measurements a number of years ago. We're working with Ivan on 9 IDB, and then when that operation changed, we shifted over to work directly with Wei at ChemMatCARS. We've got excellent collaborations with everybody involved in this over the past years. So let's start now looking at some more, if you like, a molecular level and some more crystallographic types of information from, again, some of these simple binary fatty acid systems. Now, again, these are systems which have really been studied, or at least the pure individual components have been studied in depth. I mean, you can certainly find tons of examples of fatty acids and perfluorinated fatty acids in the literature. I think Benoit published some work on some of these a number of years ago. But let's just take a look at some of the basic GIXD results from these types of systems, because I think they're relatively straightforward, but also insightful. Now, here are some GIXD contour plots for just a simple hydrocarbon, arachidic acid, in our classic perfluorotetradecanoic acid. So at low pressures, we see in the contour plot just two reflections, pretty consistent with the molecule sitting at some angle with respect to the surface normal. If you squash your film to slightly higher pressures, and of course, we basically get a single Bragg rod, molecules are pointing straight up. And of course, this is the pressures at which we start to do our deposition experiments that I was showing you previously. And so it's not surprising that we've got basically vertically absorbed surfactant molecules. So that's the arachidic acid. The perfluorotetradecanoic acid, or perfluorocarbon, is actually a little bit more interesting. So look at this. We see at very low surface pressures, this is actually very general, in this case at 5 millinewtons per meter, a beautiful sharp Bragg rod, which is oriented at QZ equals 0. So basically we've got our molecules pointing straight up, even at these low surface pressures. And again, you can squash your molecules, you can squash your films at the higher surface pressures, and this doesn't really change. And so these perfluorocarbons are excellent diffractors. They've got tons of electron density. If you look even at higher QZ, you can actually see the second order reflection. But even at the lowest surface pressures, they basically form beautiful crystals with all of our molecules vertically oriented. Effectively, I think you can just kind of take some of these perfluorinated surfactants, throw them at the air-water interface, and you'll get actually beautiful crystals without any need to compress the films. Okay, I'm showing you this data in a slightly different format here. So this is just tabulated data, but you can see really the lattice parameters for these systems really don't change as a function of surface pressure. They pack into beautiful hexagonal lattices with effectively no or pretty darn close to no tilt as a function of film compression. And again, nothing new under the sun here. Many other research groups have kind of looked at these types of effects before. Now, the mixtures, pretty much exactly what you'd expect from a perfect binary mixture, at least in terms of the GIXD results. The X-ray reflectivity was actually a little bit more complicated. But the binary mixtures, this is a simple 1-to-1 mole fraction mixture, behaves exactly like you'd expect. You see a nice vertical rod from the perfluorinated component. At low pressures, we see the usual 2 reflections from the fatty acid, squeezes up to higher pressures, and again, just 2 vertically going rods. And again, our molecules are vertically oriented at the air-water interface. And so that's why we get the types of films that we do at these types of pressures when we do deposition experiments. Now let's think about a little bit about the, if you like, the physical chemistry of the situation. What does this tell us about these different components at the air-water interface? Well, if you have a perfluorinated molecule, and never mind about the surfactant end of things yet, let's just think about a purely perfluorinated compound like perfluorohexane. If this is sitting on water, the work of adhesion of this molecule on water is incredibly small. And again, this is by virtue of the relatively low polarizability of the molecule. So the work of adhesion of, say, perfluorohexane, it's a very small number. So the amount of energy that you have to put into basically taking a perfluorocarbon on the surface of water and pulling it off is negligible, very small. Okay, the corresponding value for let's say hexane, for the hydrocarbon, more polarizable, is certainly quite a bit larger. And so what are the implications of this for a surfactant? Well, if you've got a hydrocarbon, fluorocarbon sitting on the surface, and then you've got a, hard to do this, you've got a carboxylic acid head group, which is of course a nice dipole sitting at the end of it, and put this in water, the carboxylic acid head group is going to associate with water. This non-polarizable, mechanically rigid fluorocarbon chain is going to basically just pop up like that. And so that's where we're going to get these vertically oriented molecules at the air-water interface. Okay, so that's what's going on in terms of the general physical chemistry of this situation. Can we explain in some way, shape, or form these hexagonal structures that we're seeing in the system? Well, I think we can. I think what's going on in these types of systems is that we are templating these interesting hexagonal structures, but we're not templating them with some sort of solid substrate, but rather we're templating them with the perfluorocarbon. So we're not the only people who are working on this. This is, I think, kind of been a question which is a lot of other people have been working with. And I think Phil is in the audience, and so he contributed to some of this work that I'm showing you. This is not work from my group. This is work from Felipe's group, where they've been looking at basically just pure fluorinated alcohols in interfaces. But this is really interesting. and I think Phil and Michael Goldman were kind of working on this together. They're contributing to this work. But here's a really nice, simple experiment. So what these folks have done is they've taken a simple fluoroalcohol, squeezed it a little tiny bit, deposited these down into solid substrates. And with this fluoroalcohol alone, no hydrogenated component, you still see these really interesting hexagonal or polygonal types of domains. So Felipe, who's really a kind of a master at some of these types of simulations, have run molecular dynamics calculations on these systems as well. And of course, while you can get the hexagonal crystal lattice packing of these systems at a larger length scale, this translates to a tendency for these domains to pack into these hexagonal, almost, if not microns, at least many nanometer types of structures. And so I think really the model that we all seem to be converging on is that if you have the perfluorocarbon, it's going to kind of pack into these rigid domains, these nice hexagonal or polygonal domains at the air-water interface. You kind of squash these together, and the hydrocarbons are basically just going to fit into the void regions, and they will basically be templated into forming some of these larger geometric structures that you see in the hydrogenated fatty acid systems. So I think that's the current thinking. Now, that's all fine and dandy, but it's never that simple. Okay? And of course, it's never quite that simple. So we have, of course, we don't just study fatty acids in a research group. There's no way that you could sustain your a research group that way. My group has also been doing some work with the Gemini surfactants. And the reason that we've been working with these compounds, I'll talk about in a little bit more detail in a few slides. But as part of our work, we've been looking at some Gemini surfactants. We synthesized this particular molecule here and a number of affiliated molecules like it. Now, the basic thinking that we had is that this molecule here, this Gemini surfactant, might be a reasonable proxy for basically a dimeric fatty acid. So we've got some carboxylic acids here, a couple of long greasy hydrocarbon tails here. Never mind some of these complications with the head group. We'll get into that later. But we saw this molecule as potentially being a mimic of a fatty acid. As by way of background, we were not the ones to first synthesize these, report these molecules. These were first described in the literature in early 2000. We are a chemistry research group, and so we can do chemistry, we can synthesize things. If you're curious, this is the way that you make these molecules. You basically start out with the primary alkyl amine, 2-to-1 equivalence with this coupling agent. You basically just mix these up, heat them up for 24 hours at relatively modest temperatures. Clean them up usually with a bit of column chromatography. And you can make these actually on the multi-gram scale, which will turn out to be useful for some of the applications, which I'll talk about shortly. But the key idea here is that we wanted to use this molecule here and see if this would basically give us similar types of structures as we saw with the simple monomeric fatty acids. Okay? And so what we did is we mixed this with our friend perfluorotetradecanoic acid, carried out monolayer work at the air-water interface, and the results actually looked fairly promising. And so you remember that the simple isotherm measurements for the fatty acids and their mixtures, mixed films look like this. For this hydrogenated Gemini surfactant, mixtures of these films kind of look like this. And so, of course, the dimeric version, the Gemini surfactant monolayer, is much more expanded in comparison with this simple fatty acid. It's much bulkier, but the mixtures actually look pretty darn similar to what we saw for the simple fatty acid system. Okay. So great, what does this look like in terms of structure? Well, it actually looks quite different. So in fact, we do get a phase-separated system when we're working with this mimic, if you like, this dimeric mimic of a fatty acid. But we don't see these interesting polygonal domains. We actually see round domains. And so the idea that you're templating, the perfluorotetradecanoic acid is templating these structures may very well hold for the fatty acid systems, but it doesn't necessarily hold in general. Now, I'm still kind of chasing this down the details of why this might be. Working hypothesis is that I guess the mathematicians would say a necessary but not sufficient condition of getting these hexagonal domains is the ability to crystallize your hydrogenated component. I'm not going to go into the gory details of this. I'll show you just very briefly just the GIXD results from these mixtures. But it turns out mixtures of the perfluorocarbon and this surfactant is basically not crystalline. At least the perfluorocarbon is crystalline, but the Gemini surfactant doesn't crystallize. And I think, at least in my working hypothesis, is that the ability to crystallize your hydrogenated component is actually quite important. I'm not going to go into the gory details of the X-ray diffraction data. As a little bit of a plug, Mark is putting together a really nice, hopefully a nice surface chemistry APS-based session at Pacifichem in December. And so hopefully we can talk about some of the diffraction data in a little bit more detail, sitting on the beach, drinking Mai Tais, but I'm not sure if COVID will let us. But I'll leave some of the diffraction data for a different day. Okay, so that's the direction that this work is moving into. I'd like to change proverbial gears now, kind of return back to a topic which I alluded to a few moments ago. And that is the real reason why we decided to work with these particular compounds, these Gemini surfactants. And so the real reason that we're working with these Gemini compounds, these Gemini surfactants, comes down to agriculture. So as I mentioned right at the beginning of my talk, I work in University of Saskatchewan. The province of Saskatchewan is very much an agricultural-based economy. And so there's certainly interest at the provincial level to basically develop scientific applications to agricultural problems. And so I became interested in an agricultural problem which potentially could be dealt with using a surfactant-based approach. And that is something called iron deficiency chlorosis. And so the basic idea, and it's kind of illustrated in this slide right here, is that plants, particularly pulse crops like soybeans, which are economically important in the province, can suffer iron deficiencies. And iron deficiency tends to lead to crop failures, at least very low crop yields. So you can kind of see this illustrated in this diagram here. This is showing you a field which has been planted with two variants. I know that's a bad word these days, but two variants of soybeans. Over here, we have a variant of soybean, which is genetically a little bit more resistant to iron deficiency. Over here, we've got another set of crops which are a little bit less resistant to iron deficiency. And so the soil and the growing conditions for this particular year basically made chlorosis fairly high. And so this field over here, basically the crop failed. They got really basically no crop. Over here, they did okay. And so we became interested in seeing whether we can kind of treat this iron deficiency through using surfactants. Now, what we've been working on is what's called a foliar spray. And so a foliar spray is basically just going to be a spray that we kind of spray onto the leaves. Many plants have some sort of interesting biological mechanism by which they can draw small molecules and ions through their leaves into the plant interiors. And so the overall idea is to make a foliar spray enriched in iron, which we can treat plants with. Now, a component of such a spray would include molecules that look kind of like this. And so I'm being a little bit cautious here. But the basic idea behind this particular surfactant is that we're going to have a dual purpose molecule. So the head group of this, if you look at this carefully, you realize is very similar or based upon EDTA, basically a very good chelating agent. So this bit of the molecule would bind onto iron, make iron soluble, and keep it biologically available. This bit of the molecule down here, the long greasy hydrocarbon chains, are designed to basically adhere onto plant leaves, effectively to be a wetting agent. So basically keep all the iron sitting on top of the plants and absorb the plants. Now there's going to be other components in this mixture, but that's kind of the surfactant end of at least a part of the surfactant story of this. So I want to talk a little bit about some of really the iron binding capabilities of this compound. From a more fundamental point of view. It turns out that the sprays that we're working actually work okay in greenhouse situations, field trials, maybe a little bit less so. This has been interrupted by COVID and other complications. We hope to get back to this. But let me just talk a little bit about some of the fundamental chemistry of this surfactant interacting with iron. So here's some isotherms for the surfactant interacting with iron in the subphase. So we basically got our subphase, we're loading it up with iron, spreading the surfactant at the interface. And here are the isotherms that we see. Okay. So what we see is that there is a slight response in terms of the isotherms in the presence of iron. You can kind of get a little bit more insight into this if you do surface potential plots. So the surface potential definitely changes as a function of iron concentration. With a little bit of work, you can kind of effectively tease out, if you like, electrical double layer effects. And so what we're seeing here is not simply just caused by electrical interaction effects. We're actually seeing some changes in the overall structure of the monolayer when it associates with iron. So of course, there's some excellent synchrotron-based tools that we can use for determining how much iron is interacting with our surface. So here we're using total X-ray reflection fluorescence measurements. Again, WAYS and the APS helped us out with these measurements. The basic idea here is probably well known to you folks, but we start off with essentially our Langmuir trough filled with iron-enriched subphase. In the absence of any surfactant at the surface, we reflect our X-ray beam off the surface, and we measure basically a very low fluorescent signal because there's no tendency of the iron to accumulate at the surface. But if we throw on a surfactant, which is capable of binding onto our metal, we'll see a very strong X-ray fluorescent signal. And that's precisely what we see. You can make this a little bit more quantitative. You can fit this, you can measure the fluorescence response as a function of our QZ vector, fit this with appropriate Fresnel reflectivity curves, and you can back out the amount of iron which is associated with the surface. Okay. Now, again, I'm going to kind of skip over some of the details of the X-ray reflectivity measurements, and I'll really just kind of focus on the amount of iron which is associated with this surfactant surface. And so what you'll see as you go to higher and higher iron concentration in the subphase, no particular surprise, you see that the amount of iron ions bound per head group increases. So in this case, we're working with iron 3, but the number of iron ions, it's hard to say, which is bound per head group is not 1-to-1. So normally with EDTA, you expect 1-to-1 binding stoichiometry, but that's not the case in the system. We get 3, 4, 5 ions per head group. Now, it turns out that the speciation chemistry of iron is a little bit complicated. It does have a tendency to form complexes and basically aggregates in solution. And so what we think is basically going on here is that the iron is forming aggregates and it's binding directly to the head group here. In terms of these chunks. There's actually some interesting things going on here. There's increasing amount of evidence in the literature that really the amount of iron binding, maybe more generally for iron 3+ ions, is actually largely independent of charge at the interface. And David Vackman has done some really nice work in this area as well. But really the implications of this for these crop protection applications that I've been talking about is really kind of good. And so basically we can load quite a lot of iron onto these head groups. We can basically load quite a lot of iron onto these samples and potentially deliver significant amounts, significant quantities to our crops and kind of combat this iron chlorosis situation. Okay, so that's where I kind of want to leave that particular project off for now, and maybe some more details on Pacific Hem on the beach. What I want to do now is kind of jump to my final topic. And this is returning to some of these phase-separated mixtures. So what I want to talk about now is a really interesting system involving a photopolymerizable surfactant. So I want to talk about polydiacetylene films. And so some of you might be familiar with these compounds, 10,12-pentagosodianoic acid, which is this molecule right here. So 10,12-pentagosodianoic acid, or PCDA, is a really interesting molecule. It's a molecule that if you get in close enough proximity with other PCDA molecules and you hit with UV light, you can basically cross-link. I'm kind of showing you this in this cartoon. You can basically get a polymer, a photopolymer, forming between adjacent units. Now, the photopolymer that you generate is itself actually very interesting. It has many interesting spectroscopic properties. You can make it in either a blue form or a red form. The blue form is a non-fluorescent polymer. The red form is a fluorescent polymer, and you can toggle between the two, or you can switch between the blue form and the red form if you polymerize longer, or if you apply things like mechanical or thermal stress to the polymer. So it actually has some really interesting potential applications in terms of sensing. Now, we were interested in seeing whether we could in some way, shape, or form use our phase separation approaches, so mixtures of these compounds with fluorocarbons, to pattern these optically active materials. Okay? So you can kind of get a general idea for what I'm doing here in this photograph of our booster, or rather our trough, where we've taken some of these mixtures. We've taken perfluorotetradecanoic acid, mixed it with this PDA, put this into our trough, and we photopolymerize this with our UV lamp. And yes, my Wilhelmine plate should probably be parallel to my trough barriers, but you can kind of see the formation of this red polymer on our surface here. So this is a really interesting system. So it turns out that we can get some limited control over the structures, the patterns of this material that we can form, this polymer that we can form by using this phase separation approach. So what I'm showing you here is a AFM image of a mixture of perfluorotetradecanoic acid and this PCBA molecule before and after photopolymerization. So these systems do phase separate. And if you hit them with UV lamp, you can actually start to grow in the photopolymer. You can kind of see some of these higher regions here in our AFM image, and the strand here are the red photopolymer that we're forming. And this is the fluorescence spectrum of these materials. Okay. So really interesting system. Now, we've been studying this system from many different perspectives for a couple of years. A little while ago, with our collaborators in Melbourne, we were interested in understanding some of the fluorescence emission properties of these strands. Turns out that the emission from these guys is actually fairly polarized, and so we were doing some fluorescence and isotropy mapping of these polymer strands. Now, during the course of these studies, we ran into a really interesting serendipitous result. Kind of shown in cartoon form here in these anisotropy images. But let me show you the results in a slightly different way. So these polymer strands, if you make them small enough, which you can control by juggling your composition of your film, actually show some very unique spectroscopic properties. So what I'm showing you here are some fluorescence time-lapse images of these films. We've taken some of these phase-separated films, deposited them, put them into our single molecule microscope. We've got our ultra-sensitive camera with laser illumination here. So let's get this going. So what I'm showing you here is basically the time-lapse results from our CCD camera in two different forms. And so here the microscope is in focus. Here we're doing what's called a defocusing experiment. So basically we take our image on our microscope, we move our camera a little tiny, or our microscope a little tiny bit out of focus. Now, what you see here in terms of this flashing and the interesting kind of diffraction patterns that you see in this defocused image here and here are evidence of single molecule behavior. So basically this on-off blinking and this characteristic diffraction pattern, this almost donut-like emission pattern that you see, are basically signatures of individual transition dipole moments. And so what we're effectively seeing in these larger polymer strands are individual molecules, basically small strands of this red fluorescent polymer behaving as individual molecules. So we can characterize this spectroscopically a little bit more careful. And again, in my other life, I do spectroscopy. And so this is a fluorescence time trajectory. So we're basically measuring the fluorescent signal from one of these little spots, which kind of runs along the length of this polymer fiber. And you can see this characteristic on-off blinking behavior that we see in single molecule spectroscopy. Things like fluorescence intensity histograms and on-time histograms follow single exponential population statistics, which is consistent with Poisson statistics, which is precisely what you expect in a single population of individual molecules. Things like correlation functions drop off as the function of laser power. So basically the blinking takes place more quickly as we illuminate these more with higher laser intensities. So we're basically seeing emission from individual transition dipole moments in these larger structures. Now, we had originally hoped that we might see some evidence for photoexcited energy transfer. So the idea would be that if we have two of these transition dipoles that we're measuring close by, one would start emitting, the energy would be dumped into the next, basically the exciton would hop over to our next unit, it would start emitting. So we basically see pop, 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 basically what I like to call spectroscopic whack-a-mole. But that actually didn't happen, unfortunately. There's really no evidence of energy transfer along one of these larger polymer structures certainly as a function of spatial separation. So what we've done is we've also characterized these films using GIXD and X-ray reflectivity at the air-water interface. And some really interesting things going on here. Now, The PDA system, the PCDA system, has been very well characterized in the literature in the past. There's a number of groups who've looked at it, including some of the people who attend these seminars. This is probably the definitive work on the X-ray diffraction assignments for these PCDA systems. But let's just kind of look at some results. So what I've got here is, of course, just PF as a reference sample, the usual vertical going peak. This is the monolayer of the pure PCDA films before we've done any polymerization, and we see some very characteristic peaks which you can assign according to the literature. So that's all well and good. If you take your pure PCDA film and you turn on the UV lamp, you instantly polymerize everything. Basically, the whole film turns pink at the air-water interface. That when you're really tired, you run into ways saying, "I've blown up your detector," even though you haven't. But this polymerizes really well. Now, what happens if we start to mix the films? If we have a mixture of perfluorotetradecanoic acid and this PCDA, even before illumination with the UV lamp, what you see is no signal from the monolayer, from the PCDA. So basically, we disrupt the ability to form crystalline monolayers in the system. If you hit this with the UV lamp and you start waiting long enough, you start to see a few traces of peaks which correspond to the formation of the red polymer, but nothing compared to what you get with just the pure component. And so this is not a dilution effect. This is not a case of us basically diluting the system so much that there's very little PCDA. There's a whole ton of PCDA in these systems. It's just that we're basically disrupting the film structure and impeding this ability to polymerize in a very effective way. So the cartoon picture of what's going on in the system, going back to our original picture, is that we're forming these strands of basically individual molecules of polymer in these larger structures. But the perfluorotetradecanoic acid, this very rigid matrix, basically disrupts everything. It mechanically perturbs the whole system. So we don't get long extended chains of fluorescent molecules along the entire fibers. We basically fracture them up. So we've got a series of little fractured, effectively individual polymer molecules running along the length of the overall greater structures. And so that's why we have basically independent fluorescent units in these larger structures as a whole. So basically we fracture our polymers by having this relatively rigid matrix of perfluorotetradecanoic acid sitting on top of there. Okay. So I'm starting to run short of time. Before I do that, I just want to throw up one last bit of information, really more of a kind of a public service thing. Now, we work at the Advanced Photon Source for our diffraction measurements. I'll keep on going there for basically as long as Wei and Benoit put up with me or until I retire, which comes first. But at the University of Saskatchewan, we do have a synchrotron. We do have the Canadian Light Source, and I have been pushing to try to develop capacity at the Canadian Light Source. This has been a challenge. I'm not a mover and shaker at the light source. I'm not a beamline scientist or what have you, but I'm a very persistent, sometimes quite annoying person. And so I have been pushing to try to develop and help improve capacity for measuring monolayers and related systems at the CLS. And so this challenge has actually been, some progress has been made primarily by these folks working at the Brockhouse X-ray diffraction beamline. This is Beatrice Marino. Some of you might have met her before. These are some of the capabilities of the Brockhouse line. This is a picture of the hutch at least a few weeks ago. And so we have been pushing towards getting some type of diffraction measure, GIXD capabilities at the CLS. Very recently, we have got some success. And so this are some very recent results from a couple of weeks ago, where we're measuring really a pretty simple system. We're basically measuring GIXD for basically a fatty acid film, arachidic acid that's been loaded up with cadmium, multi-layer film. But even for this system, we actually get very good signal to noise ratio. You can see all of the appropriate peaks, and you can basically measure arachidic acid bilayers in these systems. And we can actually push down to monolayers for at least solid deposited films. So the next work is a big step. We're going to try to hopefully look at some liquid surfaces. We've got the usual problem of being able to bring the beam down onto our bucket without pouring all the water out of our trough. But we are working towards this. I suspect this is going to be maybe a decades-long type of endeavor, but we are pushing towards increasing capacity there. But again, we'll always come to work at the APS as long as we're welcome. So with that, I'll wrap up. These are the folks who've done the work. The primary work has been done by the people whose names are highlighted in red. These are the folks who provided us funding or access to the synchrotrons. And I thank you very much for the invitation and for listening to me today. Thank you.